Okay, here's another one from section 8.4 the second time. If you look at the series, negative 1 to the n, pi to the 2n, over 2 to the 2n times 2n factorial, we can ask, does it converge or diverge? Does it do so absolutely, conditionally, all those things. So, to test for divergence, it's a little confusing. To test for anything else is almost impossible because it has a factorial, which is our other key to say, use the ratio test. So let's go ahead and use the ratio test right off the bat. Let L be the limit as n goes to infinity of the absolute value. Again, we're going to plug in our n plus 1s, negative 1 to the n plus 1, pi to the 2, look closely, n plus 1 in parentheses, over 2 to the 2 times n plus 1, times 2, replace the n with n plus 1, factorial. Then you flip it and rewrite the formula. So 2 to the 2n, 2n factorial, negative 1 to the n, and pi to the 2n in absolute values. And that's a fraction. Now, we should simplify all those out. We're going to notice that the negative ones just don't matter. So L is now the limit, put it right here, as n goes to infinity. Let's try comparing terms. Notice there are no x's. Pi is always positive, 2 is always positive, factorials are always positive, so we don't need our absolute values anymore either. We're going to compare like terms, so we've got pi to the 2n plus 2. I'm just simplifying the previous form. 2 to the 2n, and 2n factorial. Since 2n factorial is the easier looking one, I'm going to leave it as is. The confusing one I'm going to start to write out, but not in this step. In the denominator, I've got pi to the 2n, and 2 to the 2n plus 2, and 2n plus 2 factorial. Now I can already see that the pi's and the 2's will both have a nice canceling between them because there are 2n many of them on top and 2n many of them on bottom, and there are an additional 2 on top. There are 2n many on top, 2n plus 2 many on bottom, so we don't need that plus 2n. That many canceled out. So this is the limit as n goes to infinity of, on top, we've got our pi squared, and on bottom we've got our 2 squared, and that's all that's left of those pi and 2 terms. On the right part of it, we have a 2n factorial. Again, 2n factorial is the simpler guy. 2n plus 2 factorial, you always write the bigger one out and start. Well, whatever 2n plus 2 is, the factorial is 2n plus 2 times the next guy, which is 1 less. 2n plus 1 times the next guy, which is 1 less. 2n not plus 1. But you can always choose to stop and put a factorial because that means 2n and everything less than it. So now you see that the 2n factorial cancels with the 2n factorial. And this is all in a fraction bar. So now we have that L equals the limit as n goes to infinity of pi squared over 4, sure why not, a 1 on top, and on the bottom we have a 2n plus 2 times 2n plus 1. So now we want to know the limit as n goes to infinity. Notice pi squared is a constant, 4 is a constant. As n gets big, the denominator gets big, so the limit of the fraction gets small. What does the ratio test say to do? You're going to notice that L is a 0, and we're comparing that to the number 1. Since it's less than 1, we know that, so by the ratio test, the series from n equals 0 to infinity, negative 1 to the n, pi to the 2n, over 2 to the 2n, 2n factorial, converges absolutely. Now, we have a leading question here. If you approximate the sum by S4, how accurate will you be? I say it's a leading question because you've already seen exactly what it's going to add up to. So the question is, how accurate is it if you just stop? So if we take S4, we're going to add up A0 through A4. You want to get to the time that you're adding the A4 term. So the next time, the error is going to be A0 plus A1 plus A2 plus A3 plus A4. Now, it just depends on convention whether you stop at the 4 or you take 4 terms. I would say that we're going to let S4 mean stop at A4 so that it always lines up kind of nicely. So if I stop after 4 terms or after the A sub 4 term, and these are alternating, notice this is a positive number and a negative number and a positive number and a negative number and a positive number. We know by the alternating series estimation theorem that the error is going to be less than the next term. So whatever A5 is, our error will be smaller than that. He's the lone man out. So if you add these up and stop, your error is less than A5. So we just have to see what A5 is. A5 is negative 1 to the 5. Since it's an error term, we're going to take an absolute value. Pi to the 10 over 2 to the 10 times 20 factorial, which is pretty huge. So whatever that number is, we'll simplify it to get rid of the negative. Pi to the 10 over 2 to the 10 times 20 factorial. That is our error term. Our error will be less than that. Our answer here, S4, will be correct, give or take this much. But you know, from what we've done of Taylor's series, that this series sum n equals 0 to infinity, negative 1 to the n, pi over 2 to the 2n over 2n factorial is alternating with even powers and even factorial, so it's just a cosine. So this is cosine of pi over 2. And cosine of pi over 2, I think, is 0. So it should add up exactly to 0. All these horrible numbers that you might write out that look somewhat like this add up to exactly 0 in the long run.